Hello and welcome everyone. Welcome back to the AAVSO How To webinar series. It's really good to see all of you here today. Now today we're doing a special session all about isochrone fitting. And I know that you're as excited to hear about that as I am. But before we dive in, I do have a few quick announcements to make. First of all, we are running Zoom in webinar mode today. What that means is that you get access to a few special features. First of all, you have the Q&A button. You can find that down at the bottom of your screen. If you click on the Q&A button, you can type in questions for any of the panelists, and I highly recommend that you do just that. Please do note that you can submit your questions at any point during the webinar. If you're confused during one of the demonstrations, go ahead and submit a question right away. We are going to have some opportunities to take questions in the middle of the webinar so that you won't have to worry about falling behind. Another button, which you can find down at the bottom of your screen, is the CC or show captions button. It is not on this slide, however, it's right next to the buttons on this slide. We need to update that screenshot. When you click on the CC button, you can enable or disable Zoom's automatic closed captioning. So that's a useful one to have in your toolkit. Next up, I would like to give a shout out to our other monthly webinar series, which is sponsored by the National Science Foundation. It's entirely in Spanish, including the title, which translates to The Science of the Sky for Beginners. You wouldn't want to hear me try and pronounce it. Each webinar introduces basic science and astronomy concepts and provides opportunities for casual discussions between presenters and participants. It's totally free and aimed at the general public, age 12 and up. These broadcasts will continue to air on the third Saturday of each month all throughout 2023. Please feel free to spread the word about this series to your Spanish-speaking friends and colleagues. And now, back to the webinar at hand. Our 2023 How-To series is sponsored in full by Boyce Astro. We'd like to take a moment to thank and acknowledge them for their generous support. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right, let me go ahead and pause the screen share here. All right, so first up, we have two exciting speakers. We have Kalée Tock, who earned her Bachelor's of Science in Chemistry from Harvard University, as well as a Master's of Science from the Stanford University Department of Chemistry. She then went on to earn a second master's degree, this one in Learning, Design, and Technology from the Stanford School of Education. She's currently a science instructor at the prestigious Stanford Online High School, where she's taught astronomy for the past 6 years. Today, she teaches 3 different astronomy courses: Astrophysics, Astrobiology, and an Astronomy Research Seminar. In short, when it comes to teaching astronomy, she's a real expert. Today, she's joining us to share a very interesting observational astronomy project, which she's been running with her classes. Now, I've heard a bit about this project, and I think it's going to turn out to be of great interest, not only to the astronomers in the audience, because it's a cool project, but also to any teachers we have out there. I think you'll find that by the end of today's broadcast, you will have learned about a great new tool which you can adapt to your own classroom. Now, today, Kalée is being joined by Dr. Daryl Jansen. Dr. Jansen is an astronomy instructor and observatory director at the University of Saskatchewan. Sorry for butchering that name. He's also the author of the tool, which we're about to learn about, which makes us very lucky to have him here with us today. So, without further ado, I'd like to give a heartfelt welcome to Kalée Tock and Dr. Daryl Jansen. Welcome, both of you.
Thank you so much for that warm introduction, Lauren, and welcome to everyone. My name is Kalée Tock, and I'm an instructor at Stanford Online High School, and I'm so excited to be able to present to you today together with Dr. Jansen from University of Saskatchewan and my students, Tommy Morford, Sabine Mazzeo, Elle Mosinski, and JB Bryant. We were very fortunate to be able to use the AAVSO-NET telescopes to do a really cool project that incorporates color images, isochrone modeling, and a fortuitous eclipsing binary star. We're going to use two different websites in this webinar. The first is Afterglow for image processing, and the second is Skynet plotting for isochrone modeling. To use Afterglow, you'll need to make an account. So if you would like to follow along with that part, please enter your email into the form at the tiny URL on the slide to receive account creation instructions. For Skynet plotting, you don't need to make an account, but you're still welcome to enter your email address on the form if you want follow-up communication after the webinar ends.
All right. So one thing that I should probably clarify, Lauren, is that this was the tool that we're going to be showing off today. The isochrone tool is a big project that involved a lot of people, and so I definitely was a part of that team. But yeah, we've got a large team that worked on this tool that we're really excited to show off. So so about star clusters. So star clusters are really powerful in astronomy because they help us understand how stars work, how they evolve, the physical factors that lead to differences between one star and another, their different colors and luminosities, and their different lifespans. When we look at a star field, such as this one here, we see differences in apparent brightness and color, but we don't know whether the differences in apparent brightness, their apparent magnitudes, in astronomy we use magnitudes for brightness, are due to different intrinsic brightnesses of the stars, which is their luminosity, or because they're at different distances, or because of extinction, which is the scattering of light as it passes through the interstellar medium, and causes stars to appear dimmer than they would if our galaxy were a vacuum. And even the colors of the stars, which are related to their temperatures, may be affected by reddening. The fact that blue light actually tends to be preferentially scattered by the interstellar medium, causing stars to appear redder when their light finally reaches the Earth. So this image here contains a well-known asterism called Kemble's Cascade, with stars that aren't actually physically related. They're at different distances, reddened by different amounts, so their relative brightnesses and colors don't tell us anything about the relative luminosities and temperatures of these stars. But down on the left-hand side there of Kemble's Cascade is a picture of a star cluster, NGC 1502. And in that case, everything sort of changes. All of the stars in a cluster are at the same distance, and their light's extincted and reddened by the same amount. Therefore, the differences in apparent brightness and color that we see, that we can actually see, are due to differences in their intrinsic luminosities and their temperatures. The stars in a cluster are also formed out of the same gas cloud, so they all have roughly the same chemical composition, and that's important. It's an important factor that affects their evolution. So since the stars in a cluster are all at roughly the same distance, all their light's affected by the same amount of extinction and reddening, and they all have the same chemical composition, the main thing that leads to all of the differences that we see in this image here between apparent brightness and color is difference in mass. So for any star field, we can make a graph of apparent magnitude versus color. That graph is called a color magnitude diagram. But if we can factor in the distance and the extinction and the reddening and plot the star's luminosities or their absolute magnitudes versus their intrinsic colors or their temperatures, that graph is called a Hertzsprung-Russell diagram, or HR diagram for short. So this right here is Gaia's HR diagram of all the nearby stars. And HR diagrams are really powerful tools for helping us to understand how stars work and how they evolve. The main sequence in this on this graph, for instance, contains all stars in their first stage of evolution, where they generate energy by fusing hydrogen in their cores. Main sequence stars range from luminous blue up in the top left here, down to dim red stars. And this trend along the main sequence is primarily related to differences in each star's mass. Higher mass generates greater pressure in the core, so more massive stars end up being more luminous and having higher temperatures. But stars eventually run out of fuel in their cores. Their luminosities increase, and when that happens, and there's an increase in this outward pressure that causes them to puff up to really large sizes, and so their surfaces cool off, and they become cool red giant stars, so that we have this giant branch of stars that have moved off of the main sequence. More massive stars have more fuel to burn initially, but they burn through it at such high rates that they actually become giants before the less massive stars that had less fuel. They burn at a lower rate with lower luminosities, and they remain on the main sequence for a long time. So if we look at a star cluster where we can plot an HR diagram with luminosity versus temperature, we end up with a graph of a bunch of stars that are all roughly having the same chemical composition and the same age, but they have different masses. And it's those three factors, the mass, the age, and the chemical composition. Chemical composition is what we call metallicity in astronomy, that determine where each of those stars fits on the HR diagram. So I'm just going to switch over to the plotting tool that we're going to deal with here. So the isochrone model here on this HR diagram, which is this black curve right here, is a model that's based on our understanding of stellar evolution and how that is affected by mass, age, and metallicity. It's a curve that displays the positions of stars with varying mass for any given metallicity and age. And this tool that we're going to show off today enables us to take photometric data from any star cluster. So in this case, I've got all of the data for M67 from Gaia and APAS plotted. And then we can remove the field stars that aren't moving with the cluster. So if I click these two boxes here, it takes a minute to load. So it removes everything that doesn't have the same proper motion as our cluster, which is right here in proper motion space. And then if we also remove everything that's not at the distance of the cluster, so we end up removing a few more stars, to get rid of all of the field stars that aren't moving with the cluster and they're either behind or in front of it, to isolate just the cluster data, then we can and adjust the distance and the reddening to generate a proper HR diagram of from the color magnitude data. Then we can fit an isochrone model to determine the cluster's age and metallicity. And so that's what I've done here. And it enables us to, a good fit to the graph gives us the age of the cluster, or the log of the age, and its metallicity and reddening.
Okay, I'm not seeing any questions.
Oh, sorry, go ahead.
I was just checking to see if there are any questions, and I don't see any yet. Please go ahead, Kalée.
Great, thank you. I am going to tell you about the email that you might have just gotten if you gave us your email via the form that is accessible from this tiny URL link that's in pink at the bottom. You either got or are about to get an email that looks like this from the Skynet Robotic Telescope Network. If you didn't get one, check again in a few minutes, check spam, that kind of thing. And when you click the links in your email, you'll get to a page that looks like this, and you go ahead and create yourself an account. If you didn't get an email, or if you're having trouble registering, just sit tight for now, don't worry. The part where we use that website today will be brief. It might get distracting to follow along in real time anyway. Rest assured, as long as you enter your email into that form, and I'll link it in chat again in a sec, We'll send follow-up materials. You'll be able to follow all the steps that you see here today at your leisure later. The project that we will showcase today uses telescopes from AAVSONet, which is a robotic telescope network available to AAVSO members. For AAVSONet, after your proposal is accepted, your targets will be added to the queue by AAVSO volunteers. And from there, your observations will be automatically scheduled by ACP, executed by MaximDL. And the resulting images will be calibrated and uploaded directly to your AAVSO VFOD account for you to process. And that means that as a single observer, you just need to do two things: write a proposal and process your data. And here, to show you how simple it is, here's a screenshot of the proposal form. As part of the proposal, the observer enters a brief description of the research and the coordinates and the brightness range of the star in units of astronomical magnitude. And then the next slide shows the interface through which these images are returned. The images that are taken through AAVSONet are made available in VFOD for 3 months. The images for this project were taken more than 3 months ago, so they're not in my account anymore, but I downloaded them, so I have them on my computer. And there are separate AAVSO how-to webinars whose recordings you can watch about how to process and analyze images in VFOD. AAVSONet is available for use by member teachers. So non-member teachers or teachers with more than a small handful of students will want to look elsewhere for telescope time. If you have a larger class, you'll need students to be able to make their own accounts so that you don't have to download the images and coordinate distribution. And there are two options for that. If you teach students who are high school age or younger, you'll want to use LCO. Las Cumbres Observatory also has telescopes all over the world, and they have a large grant to support pre-college students who are just getting into STEM fields. And as a teacher, you can apply to be part of a global sky club, where you have 10 hours of time on the 0.4 meter telescopes whose positions are shown by the green dots. If you need more telescope time, you can put in a proposal to become a global sky partner. As a teacher, you allocate telescope time among your students who each have their own accounts and make their own image requests independently. And then if you teach at a university, you would not be eligible for LCO, but you would be eligible to use time on Skynet. Skynet, Robotic Telescope Network, is what some of you may have been making accounts for in the background as I've been explaining all this. In order to get telescope time on Skynet, your students need to purchase use of WebAssign, which is used with Dan Reichert's awesome Our Place in Space curriculum, and we'll send around information about that also after the webinar. For both LCO and Skynet, storage space is infinite, so students' images will live forever on the network servers, and it's entirely feasible to have school-wide observing campaigns that last multiple years, or to have students analyze images from a previous year's cohort or reanalyze images for different purposes. Today, we're not going to be using telescope time on Skynet, but we will be using its associated afterglow image processing program. And the Kumquat team, who's about to present, used afterglow in the project that they will be presenting today. So I will stop the share and pass it off to the Kumquats.
Let me just pull up my script here. As mentioned before, I'm Elma Shinsky. I'm a senior at Stanford Online High School, and I will be opening our presentation from our group. So yeah. Our team at Stanford Online High School is conducting a project that focuses on V765 CAS, an eclipsing binary system, which is a pair of stars that are gravitationally bound and orbit each other such that one blocks the other periodically and causes the brightness to have a dip. This system is in the NGC 457 cluster, also known as the OWL cluster, and we analyzed it using images of this cluster made available to us by AAVSONet, a volunteer-run worldwide network of research-grade instruments. The Madrona Peak Observatory was one of the observatories that took our images. We made a color composite image of the cluster using the SG, SI, and SR color filters, which are green, infrared, and red, respectively. S stands for Sloan, as the filters were all used in the Sloan Digital Sky Survey, which is a telescope in New Mexico, and their band passes are shown on screen. The images were first manually sorted to remove any compromised images that were too oversaturated or grainy, and we were left with 475 usable image photos for the image. It was made using Skynet's Afterglow software. The images were first plate solved, aligned, stacked, and then color mapped, SG to blue, SI to red, and SR to green. We also made an image that included the SU filter, but the SU pictures were grainy, which resulted in a noisier background. So we chose to have our final image to only have the other three filters, and SU is ultraviolet. After color mapping, we used a color calibration method unique to Afterglow to correct for extinction, an effect that happens as light is scattered and absorbed by space dust and gas as it travels through the cosmos to our telescopes. Through extinction, the light can become reddened, so it's good to correct this for more scientifically accurate color.
The photometry data from those images was downloaded from Afterglow and uploaded to the Skynet plotting program. Gaia photometric data was imported alongside it, which was used. These together were used to create two isochrones, or graphs that show a difference in magnitude in two filters versus an absolute magnitude in another. The shape of an isochrone curve is dependent upon values such as age, distance, metallicity, and rending, so the curve from the data is matched up to a distinct isochrone curve, which allows us to estimate these values. We then determined from background research that V765 is an algol or EA type eclipsing binary. This means the two stars are far enough apart to form two distinguishable eclipses with noticeably different magnitude drops. V765 had been previously categorized as either an EA or an EB. In an EB, or beta Lyrae type eclipsing binary, the two eclipses would not have been as distinct. However, all of our light curves show two eclipses, one with about 0.4 magnitude drop and the other about 0.8. The eclipses start and end at clear points and do not run into each other much. So due to this and other analysis, we agree on that classification for V765. This categorization also means that the stars are either detached or semi-detached, so there isn't mass transfer happening between the two, nor are they gravitationally distorting each other's shapes. Thus, these stars must be spherical, rather than stretched ellipsoids, which would be more oval-shaped.
In order to use precise data about our target from so many different images, we had to make sure to correct any images that were brighter or dimmer due to the individual telescopes or whether on the night that they were taken. To do this, we used comparison stars, or comp stars, that are non-variable. Thus, the difference between their known magnitude and their magnitude in the images was found and used to determine a correction factor for each image, which was used to correct the magnitude of the variable star. Photometric data, or data about the light of the star, was extracted from the images in 5 filters: SG, SI, SR, and the B and V Johnson-Cousins filters. These were chosen as they were the filters for which we had known comp star magnitudes, and measured magnitudes were plotted against phase, which is a unit of time with the curve restarting at 0 at every new period, to make the light curves shown on the slide. They all correspond with and follow the same trend and eclipse shape as each other, all of which are expected for an EA type binary.
We lost audio. Maybe. We may have lost some audio. Maybe we could just move on to the next slide.
Okay, so additionally, data was queried from both the astronomical databases ASSASSIN, the All-Sky Automated Survey for Supernovae, and TESS, the Transiting Exoplanet Survey Satellite, and used to create light curves using the same technique. The shape of these plots closely resembles those of the plots made using AAVSO-net images, thus reinforcing the accuracy of our methods and data. Our next step will be to analyze how each color behaves differently in order to gain a more thorough understanding of the color changes, and thus perhaps more specific characteristics of the stars.
Additionally, our photometric analysis allowed us to confirm the period of the system, 1.715779 days, which, although 7 seconds shorter than the previous estimate, is within the range of uncertainty of the ASSASSIN dataset. ASSASSIN uses only 2 filters, V and SG, and TESS uses their own unique filter because both projects are optimized for accuracy of magnitude measurements rather than diverse color information given by many filters. However, the AAVSO-net images give us data in 8 filters, which is particularly valuable as we now have richer color information than is usually available. This number of filters also adds to the complexity of selecting comparison stars because all 8 filters must be taken into account when evaluating them. Additionally, these analyses are a great example of all the supplementary photometric data that can be found in images that were otherwise taken with a different purpose in mind. In this cluster alone, there are over 30 confirmed variable stars that can be studied using similar methods to this. To conclude, we estimated a period for the system on par with previous estimates, suggesting that the period is not changing. And when incorporating research of previous studies alongside our light curve analysis, we suggest that the system be classified as an EA-type binary. The study, which is explained in further detail in the QR code, could not have been accomplished without the opportunities that AAVSO provides for civilian and student science, and the unique and diverse color information that AAVSO-net provides that bigger and more popular databases do not. We hope that this study demonstrates a model for future work that can be done by more students.
And so yeah, that was our presentation on our project that we completed. I will now switch over to an example of how we used Afterglow to create the color image that was shown in the presentation. All right, so I shall start over from the beginning so that it's clear. So this is what the Afterglow workbench looks like. To start, you'll want to go over to this button that looks like File Folder and click Open Files. And for this, you'll start in this Files section, and you'll want to click on Sample because our photos have all been uploaded to the AAVSO sample databases. So you'll want to click on AAVSO, which is conveniently at the top. And it's conveniently labeled webinar since that's what we are attending today. And here you'll have the 4 images. For our project, as mentioned, we only use the SG, SI, and SR filters. So you'll want to not include the SU for now. And we can open up these 3 in Afterglow. And once it loads, you can zoom out and see the uncolored image of our cluster. It looks very pretty already. So the first thing we want to do is go over to the aligner, which is 3rd up from the bottom. And you'll want to click this button, which selects all 3 images for you. And you'll want to click on reference image. So that's what it's going to fit everything to. I personally like to use the SI just to be consistent and because it's very clear. And then once those are all in place, you can click submit. And it will take a moment or two. But once that's done and it says processing is complete, all 3 of these have all been aligned to each other. And so now that they are, you can click this button, which selects all 3 of them like that. And then you can click on the 3 dots and you can click on group selected files and you can confirm. And what this does is essentially stacks them together. So you can click on this top layer. And once that loads, it will show all 3 images stacked together. And it's not colored yet. So what you'll want to do is you'll want to right click on SG. Since SG is the shortest wavelength, even though it is green, we'll want to color map it to blue. And you can notice the visual effect change in the over image. And then you'll want to right click on SI and you'll want to color map that to red. And then for the last one, you'll want to right click on SR and you want to color map that to green. And then the image that results looks a lot like the one in our presentation, but we can go even further to the display settings. So here is a histogram that shows how much light levels are in pixels for each filter. And so the peaks are the backgrounds because they're the dimmest. And the backgrounds are all currently not matched up, which means that the light might be not, not equaled out. So it sort of looks like the filter was overexposed, or, they were taken in different ways. And so it's not similar to looking at all three of the filters from the same distance and from the same vantage point. So we want to equal these out. So we'll want to first click on Color Composite Tools, and we'll want to link all layers pixel value. You'll click that, and it'll take a moment to load. And it's always best to be patient with Afterglow so you don't overwhelm it. And it does look really weird at first. It's pretty purpley. It's pretty weird. We're not really sure that stars look like this very much, but that's okay. So then we'll want to click on Color Composite Tools again, and we'll want to go to the star, which is photometric calibration, and click that. And we'll want to measure 0 points with field calibration. And down here at the bottom, it'll say in progress, and then it'll start eventually displaying a number about progress. And this does take longer than aligning, so we'll have to wait a few moments. But as soon as that's done, and we'll want to leave these 3 areas alone for now. We'll come back to those later. Just for now, we're measuring 0 points. And yeah, hopefully we aren't overloading the servers, and hopefully this doesn't take, yeah, there we go, it's loading. And then once that's 100% complete and it downloads the result, then it should hopefully but once that downloads, then we can go ahead and click the Calibrate Colors button. If my internet cooperates. Poor Afterglow, we might be overworking it. But just pretend that it is complete, and then you can click the Calibrate Colors button, and hopefully this will download, and I will show you what it looks like. It looks pretty neat. But if this doesn't download in the next minute or so, then we might have to move on. But hopefully this demo was clear, and overall Afterglow can be pretty frustrating sometimes, but I think it can create really beautiful results if you work with it and stay patient, like we are now.
So Elle, I have the calibrated image on my.
Okay, we're gonna move on.
If you want, we can move on to that next step. All right, so here it is with colors calibrated based on the G prime, R prime, and I prime magnitudes of all of the stars in the image. And so this is like a true color image of how this cluster looks from Earth. But we can actually go a step further, and that's the next thing. So Elle was going to get to this point, and then I was going to take off from here. The next thing that you could do, and I'm going to just skip over this, but we have a source extraction tool in Afterglow that enables us to extract sources from the entire image. So just run automatic source extraction and select all of the stars. And then we could run batch photometry and just select all of our 3 files and photometer all of the stars in the field, running field calibration, comparing to APAS in this case. We would use for G prime, R prime, I prime in this field. However, what we're going to do instead is actually with this tool, the plotting site, we can actually run it without a photometry file. So I'm going to copy the link actually into the chat. I think that Kalée has a document that has all of the links and everything, but here's the plotting site that we're using that I showed you earlier over here. So the OWL cluster is NGC 457, and so we can just type that in and look it up. And so here you see we've got the right ascension declination and the radius of it. To start with, I'll just click APAS and fetch data, and we can actually grab all of the APAS photometric data for that field. And here it is. One of the things that APAS is really useful for is it helps us to be able to isolate the cluster in proper motion space. So if I zoom in a little bit, it's out by just a bit. I think I found that 1.61 and negative 0.74 work the best. And then we can filter out all of the stars that are not within, say, 0.3 of that. So all of the stars that just aren't moving in proper motion, not moving through the sky with the cluster. And then for distance, the distance to this cluster is, you can actually see down here, there are 458 stars in total. But if we look for stars that are within 20%, plus or minus 20% of our distance, we can increase and decrease the value and find more or fewer stars. That number is there, it changed a little bit. And what I found is that the best distance that brings up the largest number, especially when I pull in the Gaia data for this field, is 3.14. So rather than trying to fit an isochrone model to APAS, since there are fewer stars in the APAS catalog, we can actually just pull up all of the Gaia data. And by isolating proper motion and distance at the start using APAS data, we only fetch the Gaia data that are within these bounds. So I'll pull up and I'll graph. Remember, this HR diagram is a graph of the absolute magnitude in R in this case versus the color, the B minus R color. I can frame on the data here, and I could plot, say, B minus R versus R, and in this graph frame on the model. So in order to determine this cluster's age, its metallicity, and its reddening, we already know its distance from just the number of Gaia stars that within the right proper motion bounds that leads to the largest number of stars in the field. We can adjust age. So increasing the age somewhat to bring it a little bit closer. The metallicity for an open cluster is probably closer to 0, which would be the metallicity of the sun. Metallicity is like, it's a log number, and it's the log of the ratio of the metallicity of the star to the metallicity of the sun. So 0 just means that it's roughly like the sun. This cluster turns out that there's a fair bit of reddening in between us and it. And looks like my age is maybe a little bit less. My metallicity maybe needs to increase somewhat, and or even more to bring this up. Something that I just find absolutely fascinating that's going on in here. If you notice, I'm fitting the isochrone model to the stars that run along the bottom. And the reason I do that is because there are binary star systems in this cluster, and the binary stars, they all have the same colors as single stars on the main sequence, but those points of light are brighter. They appear brighter because there are 2 stars there rather than just 1. And so binary stars tend to live above the single star main sequence. You see the binary stars there. So this particular cluster does have fairly high metallicity. It's got more metals than the sun. I think I had 7.43 and 0.27 and 0.53 were the parameters that I found earlier to fit fairly well to this cluster. So that's by adjusting these three parameters. Once we've isolated in proper motion and distance space, we can get the cluster's age. So 10 to the power 7.43 is the cluster's age, its metallicity is that, and its reddening is 0.53. Now, the thing that we can do with the reddening is we can go back to afterglow, and we've photometrically corrected the colors for these stars. So these are our photometric color correction sets the color of the star based on its photometer G prime, R prime, and I prime magnitudes. But those are the apparent colors that we see from Earth. But we have this reddening value. So if we wanted to know what this cluster would look like if there wasn't a whole bunch of interstellar dust between us and the cluster, if we go back to this color composite tools and the photometric calibration, we've already measured that, but we can add in the extinction value of 0.53 and recalibrate the colors. Takes a minute, and these blue colors are actually the colors of the stars once we've removed that reddening. Now there are some other tools here too, like we can go to the mid-tone stretch, and so that we can look at dim and bright colors better and create quite a nice looking image. Just increase the background level a little bit so that it's a little bit blacker. But there's our image of the cluster, photometrically color corrected and with reddening removed. Right, I guess we were going to end off our presentation here with some images, some other examples. So here's just another example of IC 2948, a star forming region in the Carina Nebula. So this is a set of BV and R, Johnson BVR images that are photometrically calibrated. And then we pull it into this Cluster Pro Plus tool and fit the isochrone model to it and get the reddening value for that cluster is 0.18, or sorry, 0.35 when I fit it to Gaia and WISE here. And so going back, just de-redden it and you can see how it gets bluer. There are also tools in Afterglow for adding in luminance to a luminance layer to make the colors more vibrant. Add in some narrow band H alpha and O3, so we can add in several layers, and we can even pull in catalog data like WISE 12 micron here that I downloaded from Skyview Virtual Observatory, or the 2-mass K-band from Skyview as well, or put all of them together and get an image like this that shows the warm dust in this star forming region, as well as all of the stars. There's all the filters together. Or we can take something like this M7. Here's an luminance, BV and R. I found that luminance and G prime, R prime, I prime actually does a better job of pulling out the stars that are brighter in the infrared, these red ones. We can add in WISE as well. The resolution of the WISE satellite was not as good, and so the stars end up a little bit larger, but get some colors from these warm infrared stars. or the Eagle Nebula is a nice one. So here's a BVR photometrically calibrated. It's very, very, very red, but we can remove the reddening. There's actually a lot of interstellar reddening between us and the Eagle Nebula. So that's taking out the reddening, adding in luminance, and H alpha. I didn't get O3, adding in some Ys for thermal temperatures and to mass as well. And that's everything that I had prepared to show
I
off.
love all those images. One thing that's super impressive to me that I love doing in class is dramatically being like, I think this region of the star field is interesting, and point to something that looks like nothing until you pull in the infrared data, and it lights up like a Christmas tree. It's so awesome. This tool in general kind of blew my mind, and I think is really engaging for students to work with, both for making color images as we've seen demoed here today, and also for understanding the colors and brightnesses of stars within them and what the stars are doing as part of clusters. There were some questions in the Q&A perhaps. Should we look at those at this point?
Sure. Yes. Okay. So we have had several come in, and thank you guys for providing some answers as we went along. That's been really helpful. There were a couple that probably everyone would be interested in. So there was one asked by Yewar Abbas, who wanted to know, how do you become part of a research project? How do you get to do cool stuff like this?
That's such a great question, and I wish that I had prepared a slide on it. I was bemoaning the fact that I hadn't before this webinar. So what I did is made a couple of very quick links in the follow-up links document that is further up in the chat that you can scroll up and get to, and that I'll link again. And the first one that I should mention, of course, is Voice Astro, who sponsored this webinar today. Thank you again to Voice Astro, which has a wealth of wonderful resources that I've used and many teachers have used and that many students have used to become involved in research. So they kind of accept everyone, students, grown-ups, everyone who's interested in astronomy and wants to contribute to research. And I put that in the wrong chat, sorry. Thank you. Here's the link again. And then InStar, which has also has several programs for involving students and others in authentic astronomical research, a great program for teachers. It's the one I used to become involved in this whole amazing game. And Exoplanet Watch is another one that I thought of off the top of my head because it welcomes citizen science contributions from everyone. And just as a teacher, all students love exoplanets. They love exoplanets, they love contributing. And it has many avenues to authentic research and making real contributions that help science. And there are surely more that I'll add to after I, have a minute to think about the ones that I left off and should have included. But those are the ones that came to the top of my head. And so I put links to those in that document. Oh, and thank you, Rachel. Yeah, the InStar link is in the document now, and Rachel's posting a link to that in the chat too. And Dr. Rachel Freed is president of InStar and has shepherded countless students and teachers through the process of becoming researchers in astronomy. So definitely check that out. Thank you so much for the question. And again, I should have anticipated it, didn't even think about it. Do any of the students have anything they want to add to this crazy? They've just spent this past semester diving headfirst into astronomical research, which has been, I think, an adventure. If any of you would like to add anything. They're they're still recovering.
I know that feeling very well right after a presentation. Yeah. All right. Well, thank you so much for giving that overview of all the different programs. You know, there was some stuff on there that I hadn't heard of before, so I'm going to have to be looking into it. Thank you. Okay. So are you ready for the next question now?
Sure, maybe. So I was going to pass that off to Tommy, who's working on his mic. He was going to talk about querying test data because he, with help from actually, I don't know if Bob Buckheim's on the call, but Bob Buckheim was our resource for figuring out how to query test data. And I was the conduit passing on the information to Tommy, who then actually figured it out. I saw Bob's code and couldn't understand it, and Tommy could, and then he made the whole test thing, the whole magic test data query happen appropriately. So there's a big community of practice within AAVSO that is helpful to emerging students as well. And there are certainly resources to get involved with that on the AAVSO website and elsewhere. And I have my email address also on that document. So please feel free to email me afterwards if you need more information of any kind.
Wonderful. Okay. All right. So there was another interesting question here, which I think you've touched on this already, but I want to make sure that it gets answered explicitly. So Phil Hops had asked about any guides that he could reference later on, since there's been so much good info talked about here, but it's going to be a little bit difficult to remember so much in such a short period. So for the teachers out there, where would you like for them to go look as a follow-up?
I was going to pass that to Dr. Jansen, who has the Open Press link on the follow-up site, to maybe say a few words about multi-wavelength universe. And
yeah, for sure. Did we get the link in there for that? Yes. Okay. So so this is the isochrone model and this tool that we demoed, and a lot of the features of Afterglow that we've added in, like the color calibration and all of that, they're being developed through a large US Department of Defense STEAM education grant that Skynet was awarded to develop all of these tools. And so the HR diagram project is just one module within this larger set of multi-wavelength universe labs that we're working on building to sort of that sort of comprise like a physics of astrophotography with radio and optical data university course. Everything's quite accessible to high school seniors and college and university freshmen. So at that level, and so we've the two projects that we've got mostly built at this point. The instructions are at a Pressbooks site is where we're going to be adding the rest of them in as well. But the HR diagrams one is fully written, and so you can actually go in there, and a lot of like the background section covers a lot of the stuff that I did here, but that I talked about at the start here, but in more detail. And then there's also a module on pulsars and using the Green Bank 20-meter radio telescope to observe pulsars. And so we've got those two modules pretty much ready to rip, but then there's a lot of other stuff that we've been working on this year that we'll be adding into that Pressbooks site soon. So there will be lots more to come.
Excellent. Thank you. Okay, let's see if we want to maybe switch over. Tommy, if you're there, there was some stuff that you wanted to say about the test data, right? Is now a good time for that?
Maybe he might have just reconnected. Tommy, are you? There are 3 Tommies now.
Yes, I believe. Okay, just to test. Is my microphone working now?
Yes,
Yes.
it is.
Okay, yay, that's a surprise. So let me just figure out how to screen share here. Screen share that. Yeah, so querying tests is an interesting ordeal. So AstroQuery is the library that's typically, wait, I think I'm gonna mute. There. So AstroQuery is the library that's typically used for that. However, there's an incompatibility with the data format between TESS and some various other sources. So if you want a light curve from TESS, then you have to go through the light curve library for Python, which modifies the data in a certain way. So that was what I initially did, which if you can see my screen is that. And that works, but it's slow, which I didn't like. So then I rewrote it. So that's my version, which uses MAST directly and just queries it instead of going through AstroQuery or any sort of Python library. Basically, we can just run this for target with a time and a period of that and name. And then one of these is a PNG. That's not the PNG. That's not it either, apparently. There we go. That's a PNG, which gives us a light curve essentially.
Very, very cool. I'm
It
really
is-
impressed at how you rewrote that.
Yeah, and we were stuck. We literally spent weeks on this before we got some magic information that I don't even really understand what it was from Bob, which Tommy was able to make it run in Colab, and we can share. There's the link to the Colab. Thank you so much for that, Tommy. All of my research teams have used that, and it's great because you can enter in the coordinates of your target and get pictures like this out of it, which is greatly facilitated lots of stuff. I see a few more email addresses coming up in the form, so I'm going to create those accounts. And I think there were a few more questions, including one request for Daryl to go through the workflow pulling up Afterglow.
Yeah. So I'll just I'll do Chuck's question here first. So you asked about, so Chuck asked about the blue stragglers here and whether Afterglow identifies them. So there's a save data button that you can see right here. There's also lock cuts. So these things
Wait, you need
sorry,
to
I'm not sharing my screen. Thank you. This one again. Okay, sorry. Here's the blue stragglers that I think Chuck was asking about. So first of all, 21,000 stars data points we pulled in here, and there are only 615 apparently. Oh no, that would be the APAS. But there are only a couple of thousand. To get as you're sort of moving these sliders, trying to move these sliders around, things get really bogged down when we have this many data points. But when you have the plus or minus ranges set, you can then actually click this lock cuts button, and that speeds everything up. So I clicked it there. Took a minute, but it locked everything, and so now I think, what was this, 9.61? Everything's a little bit more responsive without so much data being displayed on the graph. But also now that I have just these 1173 stars, I can click the save data button, and it produces two CSV files. The one is the model, so that's actually the points on the isochrone model. The other one though is scatter, and came up on my other screen here. And so this has the magnitudes and right, all of the data that are included, APAS, all of the catalog data that's on there. So yes, in theory, you can actually comb through here, use sorting in Excel to determine what are the, in this case, I would just I would calculate B minus R and magnitude, and then just sort that column to get the bluest values, the smallest values, and then we could get all the right ascensions and declinations of all of those stars. And then you could go to your M67 images and you could actually figure out which ones are the blue stragglers and identify them that way. So yeah, definitely there are ways of doing that. So, and then Patrick asked for another demo of my workflow, which yes, which I ripped through rather quickly. So this is so much fun to do, this one. So there is, and I can tell you about one thing that's not working, or two things actually, if I do it this way, that aren't working right at the moment, that we have to fix up. So if I type in M45, the Pleiades, and look it up, for some reason, we haven't been able to sort it out. Our catalog lookup, the radius values are off. M45, though, I don't know, you put in something like 2-degree radius. The Pleiades is huge. If I then say, oh, I want to, well, let's start with APAS because Gaia is going to be way too many stars. Click on APAS and click fetch data within a 2-degree radius. We should get an error message that the Vizier query failed, because what happens when I fetch data is it actually pulls from the APAS data set, but then matches with, based on right ascension and declination, based on the star's position, it matches with Gaia so that we can get the Gaia proper motion and distance values for each of the stars so that we can then filter them out. And so the workflow for a large cluster is actually to start off with a little bit smaller radius and use APAS. We can fetch the APAS data for M45. And it looks something like that. And on the proper motion graph, I can zoom out and, oh, right there it is. There's that's actually the cluster's proper motion. It's a nearby cluster, so it's moving rather rapidly in the sky. So the values are something like 20 and minus 45.77, 20 minus 45.77, something like that. And then I can filter, say, something like this. So 20 plus or minus, well, we could say 4. There aren't going to be a lot. And then the distance as well. I think the distance to the Pleiades is something like 0.12, 120 parsecs. And so then now with our filters in right ascension and declination, motion in proper motion in RA and dec, and the filter for distance set, and we've found the distance and we found the proper motion. Now we can look up Gaia, and the fetch data will only fetch the Gaia data at within 5 degrees of this position in right ascension and declination that have proper motions that are in this range and distances that are within this range. The other thing that's not currently working is, for some reason, the 2MASS and WISE lookups are not applying these filters properly. So we're just working on that. But Gaia does work, and APAS does work. So we can fetch all of the Gaia stars within 5 degrees, which is way too big, that are within these proper motion and distance bounds. And then I can plot I can plot B minus R versus R and get a nice HR diagram of the Pleiades, with all of its stars, showing that the Pleiades, actually, if I change this to Gaia, then it just shows the Gaia numbers. So yeah, showing that there are about 1,100 or so stars in the Pleiades. So according to Gaia and the cuts that I applied, which maybe I should make this more like 20%, and I could fiddle with this, but and you can also see, you can see the binary stars. Gaia is beautiful because you can actually often pick out the binary stars really nicely, and also the main sequence, and so we could then adjust the age and the metallicity and the reddening. Which there's not going to be much reddening.
Yeah, it's really great because you don't even need data. I mean, it's great if you can incorporate your own data, right? Your own images, but you can also take your own images and compare them. Like you can have one of the isochrones be your images and one be images coming from APAS or from Gaia. So it's really great as a source of being able to look at multiple things at once. There was one question that you were maybe gonna address about blue stragglers.
I did that one.
Oh, you did. I'm sorry.
Yeah, that's about the blue stragglers.
Yeah,
I think what I said there should be enough. But what the one thing that you brought up though about, you know, whether we use the Gaia data or we use our own photometric data reminded me of one of the questions here that I had responded to in the Q&A. That's probably worth discussing. Richard Wagner asked, are you choosing your demonstration clusters carefully? I've tried pulling HR diagrams from clusters from my own BV images, but find that many don't show up very distinctly in Gaia distance or proper motion plots. And I see. I guess I didn't really answer your question properly. But the thing that I was going to follow up with and just say some more words on is that, yeah, there are 4,000 known clusters, and sorry, I cannot be sharing my screen. Just go to this. There are 4,000 known clusters, and some of them, the Gaia data just aren't very great. Like the distant globular clusters, Gaia's photometry isn't yet wonderful for those. Or a lot of the clusters that are in the Milky Way are kind of difficult to dig out with Gaia data. And sometimes if we get good images, good quality photometry from our own telescope data, seems to sometimes work better. Still having the ability to match our photometry to Gaia's proper motion and distance values is helpful. But you know, it's good using as many pieces as we can.
Okay, thank you for bringing that one up again. I think that was really helpful. So it looks like we're getting down almost to the end of the questions. We did have one come in asking about what survey you would use for a source of high quality infrared data, near infrared and mid infrared. Would you use Gaia for that, or would you use something else?
Yeah, so Gaia only images in that BP and RP filter. So so not that, but the two surveys that we have on the tool are 2MASS and WISE, which are both infrared, sort of a range of infrared magnitudes. So so using those, especially once we get there's actually there's lots of really interesting stuff to look at once we get a couple of those bugs fixed with those ones, so that we can see all of the stars and not have to limit our radius.
Okay, great, thank you. So last call for questions in Zoom. I'm going to go ahead and check over on our Facebook live stream and see if any questions came in the past couple of minutes. Okay, I'm not seeing any questions on Facebook, so back to Zoom. Anyone got anything? No. All right, it seems like things have been pretty well covered now. So I think I'm going to go ahead and call the end of the Q&A. Thank you, everyone. Let me go ahead and put up our closing slide here. Final announcements, all that jazz. All right. Now, first and most important of the final announcements, I would like to extend a heartfelt thank you to Kalée, Dr. Jansen, Elle, Jacob, Tommy, and Sabine for sharing their time and knowledge with us today. This has been just a wonderful session. Thank you guys. I could tell you put a lot of work into rehearsing this and making it perfect. So it's been wonderful. Thank you. I would also like to thank again our series sponsor, Voice Astro. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. And today, I would also like to express a special thank you to everyone who's here in attendance. Your excellent questions really did help to turn today's session into something special. Even more than that, your participation in all of our programs is what allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you. We're so grateful for your support. Now, I have got some good news for those of you who are asking about wanting to reference all of the wonderful information that's been shared in today's webinar. Today's broadcast has been recorded, so you'll have that recording to look at in addition to all of the excellent follow-up links. The recording is already available on our Facebook page because we've got that automated system set up. And pretty soon, we're going to upload the recording to our YouTube channel as well. If you head over there to our YouTube, you can find us under the username AAVSOHQ, and we have a whole library, many years of monthly webinars available for you to read about or to watch. I got a little too far into the library metaphor there. All right. One last announcement. When you log out of this webinar, you should be automatically shown a survey. It's got just a couple of questions on it. I would really appreciate it if you could fill out that survey. Let us know what you thought about today's special edition webinar and anything we could do better next time. I'll be keeping an eye out for your responses. All right. To close, I would like to express one last huge thank you to all of the speakers from all of us here at the AAVSO. We really appreciate you.